about the interpretation of calibration certificates. Because of time, we're supposed to start about 4 minutes ago. I'll quickly ask the radionuclide manager to introduce himself so that we can start with our presentation of the day. We've got a limited time, unfortunately, so we had to hit the ground running already. May I allow you, Nico, to welcome everyone so that we can proceed with our business of the day.
Thank you, Itole. Good morning, everybody. I'm Nico Ice. I'm currently acting deputy manager for the radionuclide division of SAHPRA in radiation control. From my side, I would like to welcome all participants to this webinar on the interpretation of calibration certificates. A special welcome also to the presenters, Ms. Wendy Toka and Mr. Marius Ramatsitsa from Nexa. Ms. Wendy is from NEMISA. Calibration and radiation measuring equipment is not only a legal requirement, but certainly good practice to follow as part of the radiation protection program. Calibration is not just a procedure to follow to see if your equipment is still working fine, to see if accurate measurements are obtained for specific applications that is intended for. That is part that we will elaborate more on the presentations today. I really hope that the presentations will satisfy your expectations. Time is set aside in the program for questions. Please make use of the opportunity to clarify any uncertainties. Colleagues and participants, I really hope that you enjoy the presentations and have a better understanding of the information displayed on your calibration certificates at the end of the day. With this, I hand over back to Titole. Thank you, everybody.
Thank you, Nico. Just a few house rules. Please note that we will be recording the session, and the recordings will be available on our website. At the end of the presentation, I'll quickly try to show you how to access the recording. And we have defaulted mute your camera and your mic for order. For any questions, you're welcome to type on the chats, and then after the presentation, we'll able to have those questions solved through the questions so that our presenters could be able to attend to them. Then I will quickly then ask Wendy to give a presentation. Wendy, please let me know if you are able to see your presentation this side so that you can quickly start on it. Wendy? No, Wendy? Maybe you are muted, Wendy. I cannot hear you. Ntokozo, can you hear Wendy?
No, we can't, but she's not muted, so I'm not sure what the issue is. We can't hear her.
Wendy?
Wendy, maybe try taking your speaker volume up. See if that works.
Wendy, are you around? You are now muted, Wendy. I think Wendy, she's struggling. I will have to move to the next presenter, unfortunately. She will have to do the second presentation. We'll just alter our presentation for now. Marius, are you ready, sir, to give the presentation?
Yes, Gitole, I couldn't hear what you were trying to say.
I was saying that our first presenter seems to be having some challenges, so I will ask you to give the first presentation in the interest of saving time.
Okay, right. No,
I'm projecting your presentation now.
Don't worry, I will project it from my side because I've already updated it.
Okay. Please do so, sir.
Okay. If you want to project, then you will have to project the one that I actually. Do you see something?
Yes, but you haven't opened. I see your drives. You haven't opened your presentation.
I did open it. Let me. Do you see it now?
No, sir. It's not the presentation that shows.
What
drives?
Is
I'm
what?
seeing your drives. Maybe.
Oh, you don't see it now.
No. I can see your drives. I see a lot of documents on your drives, but the presentation, it doesn't show.
Okay, let me do this. I see where the problem is because what do you see now?
It's still your drive, sir. You're not projecting your presentation. It's not open yet. Can I assist you on my side in the interest of time, Dr. Maras?
Yeah, I emailed you open the one that I've just emailed you now.
Okay.
Yes. But I don't know why. When this is back, I can see her.
Wendy, are you able to?
Okay, can you hear me now? I just rejoined.
Yes.
Okay,
yes.
No, probably there was something wrong with my audio on the side. Sorry about that.
Okay, no, thank you. I'm going to project your presentation. Let me know if you're able to see it so that you can be able to proceed.
I can see it. Thank you so much.
Yes, you can take over, ma'am.
All right. Okay. Good morning, everybody. I'm Wendy from the National Metrology Institute of South Africa, and I will be giving a presentation on metrological traceability and calibration certificate interpretation. So I'm just gonna switch off and then I'll ask Ditole for you to move on to the first slide. Thank you. All right, thank you, Ditole. Okay. The thing that we need to start with is to ask ourselves, what is this term traceability? The metrological traceability, in short, traceability, according to the International Vocabulary Metrology of Metrology. Sorry, can you please, I see something, not my slide. Ditole, oh, thank you so much. Traceability is a property of a measurement result whereby the results can be related to a reference through documented unbroken chain of calibrations, each contributing to the measurement uncertainty. So if we look at the definition of traceability, you can see that there are three things that we have to look at. One being the calibration, second, the reference, and third, the measurement uncertainty. So when we're talking of traceability, we are actually looking at a measurement that is a quantity that actually links the measurement to the international community. Ditole, can you please go to the next? Ditole? Ditole?
Oh, you want another slide?
Please.
Yeah.
And then we can now go further and ask ourselves, why is this traceability important? The answer to that would be traceability is essential in ensuring consistency, reliability, and most importantly, the quality of measurement. And then we ask ourselves, how is this traceability maintained? Please, you can go through, you can move the slide to the toilet. So how do we maintain traceability? In terms of us as the laboratories or the National Metrology Institutes, we maintain traceability in 3 ways. We participate in international comparisons. We calibrate the national standards routinely at primary standards laboratories. And we also do monthly verifications of the national standards by performing beam output measurements for the standards that we have as the lab. So in terms of participating in the international intercomparison, what happens is that we have to have some degree of equivalence to the international standards or to the SI unit through the international comparisons that are organized by the regional metrology institutes. In our case, in Africa, we have the intra metrology system, namely the AFRIMEX. But there are globally other metrology RMOs. For example, we have the GulfMet, which is a metrology, it's a metrology RMO in the Middle East, like in the Gulf. We have the Euramets in Europe. We have the APMP in Asia. We have the COMET also in Europe. We have SIM in the US and AFRIMEX, as I mentioned, in Africa. So how do we ensure that degree of equivalence? What we do is that an RMO will organize an intercomparison where almost all the member states or the national metrology institutes that are part of that MRO will have to participate in that and ensure that they have some sort of equivalent in the form of a measurement and its associated uncertainty. As I mentioned in my first slide, I mentioned the word uncertainty. So uncertainty is actually any measurement without uncertainty is incomplete. So then we have to then ask ourselves, what is this uncertainty? Uncertainty of measurement is the expression of statistical dispersion of values attributed to a measurement quantity. And all measurements are subject of the uncertainty of measurement. And a measurement result is only complete when it is accompanied by a statement associated with uncertainty. Ditole, may you please move to the next slide?
You want another one, ma'am?
Please. Okay, then now. Then also in my first slide, I mentioned the word calibration. Then we ask ourselves, what is calibration? Calibration is a quantitative determination under a controlled set of standard of conditions of indication given the measuring instrument as a function of the value of the quantity the instrument is intended to measure. So in simple terms, we can say calibration is the comparison of the unknown to a known with an associated uncertainty. When we say the known and the unknown, the known, we are referring to the national standards that is kept and maintained at the National Meteorology Institute of South Africa. And that standard also is used to participate in the international comparisons to ensure the degree of equivalence to the international community. And then the other question that we need to ask ourselves is, why do we have to calibrate the instruments that we use? We need to calibrate them in order to ensure the reliability and accuracy of measurements in all ranges and for all ranges that the instrument is expected to work properly. We also need to calibrate our instrument to ensure that the instrument functions reliably in the dose range specified. So when I'm talking of the dose rate, I'm actually referring to us in the radiation community, because these can be in any range of measurement. But in radiation community, we're speaking of the dose rates, we're speaking of the exposure rate. So hence I use the word dose rate. And we also perform calibration to confirm the performance of the instrument under extreme environmental conditions in which it is certified to perform satisfactorily. Vitola, can you please move to the next slide? Okay, then after asking ourselves, why do we have to do that? We then have to go further and say, when do we have to calibrate our instruments? We need to calibrate our instruments upon receiving, when we get the new instruments, immediately when we get them, we need to calibrate them. We also need to calibrate the instruments after they have been repaired. One thing that I think I should mention at this stage is we shouldn't confuse calibration with repairs, because we have realized that sometimes one would think that when we do the calibration, we are actually doing some repairs on the instruments, or we are performing some adjustments or something that has to do with the repairs. That is not what we do in the calibration. The instrument needs to be repaired by a certified body, and then after that, taken for calibration. And we also need to calibrate our instrument periodically to ensure that they're still functioning properly, and also to comply with our regulations. Next slide, please. Ditole?
You need another one, ma'am, okay?
Please. Okay, then we can now come to how do we then perform this calibration. There are techniques that are outlined in the IEA Safety Report Series number 16, that as the labs we use as the guideline when we are performing calibration. So in this presentation, I'm going to show the 4 techniques. However, I'm going to dwell on the technique that we use as NEMISA, which is technique number 4. But then here I'm just showing that we have different techniques. Vitola, can you please just go a bit up? Because we have like 4 techniques that I need to show. You are on number 3. If you just go a bit up, I need to show method 1, 2 before we can go to number 3.
Is this one okay? This is method 1?
No, this is method 3. Just go up a bit.
I'm showing method 1, and this is method 2. This is method 3.
I
This is
see method 3. So
um,
I need to see where it starts, because there are different methods that we need to see. So what I see is method number 3.
Ntokozo, can you confirm on your side? Because on my screen, I see method 1, calibration techniques method 1.
Method 1 on my side as well. Maybe just give it a sec.
Yeah, maybe there's a delay on your side, man.
Yes, I think there is something that happened. Okay, no, it's fine. So yes, there are those 2 methods that are presented, because I only see method 3 here. I'm not sure what's happening.
Yeah, on my screen, it's definitely method 1 that is displaying.
Okay. Okay, can you then just move to method 3 and 4 so that I can dwell more on the other methods? So those
Okay,
ones are.
Okay,
Yes.
I'm on method 3 now.
Yes, I see method 3.
Yes, you can.
That's
you
what
can
I've been seeing.
Yes, I just changed now. Wendy?
Okay, so now it's okay, Ditola. I can just move quickly to method 4 that we are using, which is a method where you can move to method 4, it's fine, because the 3 was just to show that we are having 4 different techniques. So now we are going to look at the method 4 that we are actually using in NEMISA, and I believe that it's something that is actually practiced in the labs in the country. So method 4, what is it, is that we are actually calibrating the instrument that is brought in to the lab using a known radiation field. What do we mean by a known radiation field? So what you will have, we are actually the standard, because now, as I mentioned earlier, calibration, we're comparing the known to the unknown. So in this instant, the known will be the source, which means is the amount of radiation that is coming out of the source. And this source has been characterized by using dosimetric method to ensure that the amount that we say is giving is correct. And by using that method, we are actually using a calibrated standard, which is our national standard, to characterize the beam that we have. And we determine on different distances the amount of dose rate, or rather the ambient dose equivalent rate, or the exposure rate that is going to be displayed as a true value. And then the unit under test, which will be the measurement instrument that is brought in, will be directly compared to what is being given off by the radiation source. Can we move to the next slide, please? Please, if I'm moving too fast, you can request that I slow down wherever you feel that I'm moving too fast.
No, you're fine, ma'am. Just be mindful of time as you deliberate.
Yes, because I'm actually looking at the time that I'm only given 40 minutes, and already we have taken some time. Okay, we can move to the next slide, Victoria.
I'm on the calibration certificate now. You need another one.
No. I'm seeing there's a delay on my side. Okay, I just see the calibration certificate. So in doing that, after the calibration, we actually need to give a report in the form of a certificate, or in the form of a certificate in terms of calibration. And if we have been performing the tests, then we will give a test report. And then why do we have to give this report? The reasons for that is we need to report to the customer the results of measurements that we have obtained. We also need to demonstrate in that certificate that the instrument is actually complying to the specification limits. And we also need to demonstrate traceability to the international system of units, which is the ISI units. We can move, Ditole.
I'm on the next slide.
Actually, I'm seeing on my side, the slides are a bit delayed. So I'm still on the calibration certificate on the objectives.
I'm on the requirements now.
I don't see that. I'm still seeing okay, no, it's fine. I can just talk to that even though I'm not seeing it. Okay, and these for the certificate, there are requirements that are stipulated in ISO 17025, which we comply to as we are accredited. In this presentation, I actually show the minimum requirements, and I'll also talk about the other requirements as we go into the certificate itself. One of the requirements are as follows. The certificate must have a title. It also have to have a unique identification, which should be displayed on each and every page. There should also be a method that's to show the customer how the instrument was calibrated. There should be a calibration and issue date, calibration results, preferably in table form and with associated uncertainties. There should be a traceability statement. There should be environmental conditions under which the calibration was performed. The statement indicating that this is the end of the certificate. There should also be a calibration interval only when that is required by law. If that is not required by law, as a calibration lab, I am not supposed to stipulate the calibration interval for the customer. I can only put the calibration interval upon request by the customer or whenever there are regulations around the calibration interval, in which in our case we have the calibration intervals as stipulated by the regulator, which is SAHPRA in this case. And also, there should be signatures of the person who performed the calibration and also the approver. And in other instances, like in the instance of NEMISA, you will have three signatures, which will be the person who performed the calibration, the checker, as well as the approver. The reason why there should be signatures at the end is that the calibration certificate has some legalities around it. So then it should show that there should be some form of responsibility and accountability. Hence, you see the signatures, and also there should be traceability to the person who performed the measurements. And the person who performed the measurements should be someone who has been declared competent. And also, in the accredited labs, the person who takes the responsibility of the measurements is the person who has been deemed competent through the assessment that is performed by SANES. And then what are the responsibilities around? Why do we have that? Is because the certificate can be used in a court of law whenever there are some disputes relating to the performance of the certificate, of the instrument, or the results on the certificate. Okay, Ditola, you can move to the next slide, please.
Wendy, I'll request that you run through the measurements because we really
Yes, that's why I'm asking for us to move to the next slide. So as you can see here, oh my word, I'm not going to
try to expand it.
Please do.
Let
Yes,
me know
as you look here, so here, this is a form of certificate that you get that is actually complying to the minimum requirements that I have spoken about in the previous slide. So here you will see where the calibration has been performed, the title and everything that has been needed. And also there is a procedure that shows how the calibration was performed. Ditola, can you please just continue with the slides so that we can run through the measurements? Okay, before we talk about the measurements, also on top there is a statement of traceability that actually speaks to that these measurements are traceable to a national standard that is maintained on a monthly basis, that is also used in the international comparisons to make sure that we determine the degree of equivalence to the international community. So in the measurement results, because we, for example, as we calibrate the survey meters, we are traceable to AirCamera, which its units is the SI unit for our dosimetry measurements. And AirCamera's unit, which is a gray, which is simply just a joule per kilogram, is then now being used as the traceability of the measurements that we have. And in this case, we're looking at the calibration of a survey meter that was calibrated not in AirCamera, but in ambient dose equivalent rate, which is an operational quantity that was derived from the AirCamera by means of the conversion coefficients as are shown in the table for different radionuclides. For example, when we use cesium, we have a conversion coefficient of 1.20. And for americium, which we use only for the energy dependence, we have a conversion coefficient of 1.74. And then if you see this certificate, you can see that there are some requirements that need to be conformed to. And this instance, you see some stars there that shows that there's some form of non-conformance in the measurement results. Ditola, you can also move to the results so that I can just run through the measurement results. Okay, so in the certificate, as I mentioned that the certificate should have measurement results, preferably in a table form. This is how the NEMISA certificate will look. In the certificate, you will see the units that were used for the calibration. You see what the source that was used, and also the measurements as they are. And then we have two sets of results, where now the comparison come in. You see on your right-hand side, you have a true value. The true value is the value of the dose or the ambient dose equivalent rate of the source that comes from the characterization of the source. And then on your left-hand side, you will see the readings or the measurement results from the unit under test. So as we look at this certificate, for example, if you look at range number 1, this is on 50 millisieverts. You can see that there is some form of non-conformance. why do we have these stars? We have two requirements that our instruments have to comply to. Number one being, on each point of measurement, the measurements must not exceed 25%. So which means that the percentage difference between the true value and the results from the UUT should not differ by more than 25%. That's why you'll have the 3 stars. And then also, we use the 2 stars, which shows that per range, when you combine the 3 points of a range, because we are actually calibrating per range, where we choose 3 points, then we look at the 80% of the maximum value that the instrument can get to, the 50% of that, and the 20%. So in that range, when you see the 2 stars on your certificate, it means that the average of all the points differs with the true value by more than 15%. Hence, you will see those double stars. And as well, on your right-hand side, you see that you have your uncertainty. And as I mentioned earlier, that no measurement result is complete without uncertainty associated to it. So what it means is that the measurement value that your instrument had read, it's within a range. You can read from 45.5 minus the 6% of that, and also, so you move from, there is a range, so it's from the minus to the positive. You minus what you see, and you can also add 6% to what you see, and then it gives you a range that says your instrument is okay or works perfectly at this range. And with the uncertainty, you will see as we go down, you will see a certain term that we use, confidence level. That means that we are 95% confident that your measurement, that your instrument reads this value to this uncertainty. And for that, we assign a factor of 2, which goes with the level of confidence. Is there anything that, okay, so if you look at these, you can see that there are 2 ranges where there are some non-compliance, which means that when we look at this instrument, on the higher range of the instrument is not really performing well. And also at the lower range is also not performing well. So when you use the instrument, then you have to be aware that at this range, your instrument is not really performing well. And you will then decide whether to use it or not use it, depending on your requirements. Okay, Ditsola, we can then move further because I've run through the results. And also there, you can see that we spoke of the aberration. When we actually calibrate in terms of aberration, we're not really performing the whole range of measurements like we do with cesium. The only thing we're looking at is, can this instrument work at energies below 60 kV EV, or when you use the X-rays, depending on how you use your instrument. Because sometimes there are instruments that need to be calibrated in X-rays, and you find that there are no facilities to calibrate in X-rays. So the americium will also just help you to give an indication that the instrument that you use can be used for X-rays and also for gamma rays of energies below 60 keV. And then, as well as you see there at the bottom, there are signatures of the people who have done the measurements. As I mentioned, it's a legal document, so there should be some form of traceability to the individuals who have performed the calibration. Litole, you can move again. Litole?
Yes, ma'am, I'm on the remarks on the last slide of your
Yes,
page.
so also, as you can see, as I mentioned, the 95% confidence, we also mentioned the environmental conditions at which the instrument was calibrated. In this case, is 22%, 22 degrees, with an uncertainty as well. As I mentioned, that no measurement is complete without uncertainty. As you can see there, we have 22 degrees, but we allow an uncertainty of one degrees. This means that in our lab, in each and every hour, we cannot let the instrument, our temperature, to increase or decrease by more than 1 degree. And also, we look at the humidity conditions, in this case, which is 43%, at an uncertainty of 15%. So I think this is all. And then at the end, you'll see that statement that shows these is the end of the certificate. With all being said, I thank you so much. Thank you.
Thank you, Wendy. Thank you, Wendy. We'll allow the last presenter, and then we'll take questions at the end of the presentations. I hope there are questions on the chat. And then after the last presenter, we'll do so. Marius, you are welcome, sir, to take over. I hope that your slides are visible, or you are able to present on your site.
Okay, thank you, Ditole.
Should I project it on my side, sir?
I'll prefer to load this from my side.
Okay.
And then let's see if let me, in case if then there are some challenges, that's where you will come in.
Yes, you are welcome to project on your side.
Okay.
In the meantime, please, colleagues, you are free to load your questions on the chat. We'll have a session for questions after the presentation. So please feel free to write your questions so that we can be able to take them after.
Okay. Do you see something, Ditole?
I'm seeing your drives. Your presentation is not loaded.
It looks like. Okay, yeah, because I'm actually, let me try it for the last time. If it doesn't, that will then have to look at. Do you see something now?
No, no, sir. Do you have it open on your site?
Yes, it's open. And I'm wondering why I cannot see.
Just have it open, and then you start sharing your presentation.
Do you see it now?
Yes. Please put it on the presentation mode.
Okay, right. Okay, thank you, everyone. My name is Marius Ramashija. I work for NEXA. I've been in this field for ionizing radiation dosimetry for more than 18 years. I started this from Itemba Lab up until this whole experience was acquired from Itemba Lab, Tygerberg Academic Hospital, Nuclear Medicine Department, and also NIMISA, National Meteorology of Institute of South Africa. and a South African Bureau of Standard, and now currently I'm working for NEXA. Thank you. This is what I'm going to talk about today. Also to assist with the interpretation of our with the interpretation of the certificate and measurements results, which is actually a key. And this is my talk outline. I will actually first take you a bit backwards to what is science of measurements and where legal methodology comes in, then introduction, and the purpose, why are we performing calibration, and why is it so important for us to do that, and the instrument maintenance. Selection of instrument, it will be touching based on what do you need to measure when you want to procure instrument which is fit for certain purpose. And what nucleus do we need to measure? That determine the selection of the type of instrument, the types of ionizing radiation, and the types of radiation detectors, and the calibration requirement, the instrument calibration, and the traceability chart, just a high level, as my colleague Ms. Toka already covered a lot from that. And what is actually a science of measurements? If you look in your surrounding, meteorology is part of our lives from birth. We cannot live without meteorology. Even if you look the safety treatment, when you go for x-rays, that is, you are talking the science of measurements. When you go to the technical evidence, everything needs to be measured accurately and safely. That is the science of measurement. The seafood needs to be analyzed, and we collect the data. That data gives us an indication of the safety of the food that one can eat. And the healthcare, all those MRI, they are also portraying a very crucial role in the science of measurements. And those measurements also needs to be dealt with or include the measurement uncertainty in order for you to get the accuracy measurements. If you look everything, globalization, you look innovation, climate change, everything is meteorology. You look at safe traveling, there is a meteorology playing a part. Meteorology is playing a part into that field. If they don't have accurate calculations, we're going to have so many planes crashing to each other from the atmosphere, from the space. And then the regulation, when you pour the fuel from the car, you are not sure whether the 20 liter goes into your tank. But now, based on the fact that there's a regulatory body which deals with that, and the science of measurements also plays the role that whatever the quantity of the liters, it must be equivalent from the pump as goes to your car. And that one we can give you the assurity. There's the baby food. There were some times where they've got some other few elements which were eventually affecting the infant. And the science of measurements plays a crucial roles. Even weighing the baby from birth, checking the development, all those measurements which are done, they also determine whether the abnormality and the growth of the baby. What is legal metrology? Legal metrology is the law enforcement to make sure that everything is calibrated. All our equipment are well maintained. All equipment are approved for their purpose, what they are intended for. Speed traps cameras. Speed traps cameras must be actually calibrated because this is the key or the killer in our society. And if you look at when you go to the butchery, you buy a steak of 10 kilograms. If the scaler is not calibrated, it means that we as the consumers, we suffer the consequences. When we go to the hospitals, most of the device were not actually calibrated, but these days we could see that now things are now changing, and we do appreciate for that part, because most of those instruments, they actually carry a huge decision. Unlike when you go for you to check the BP from the blood flow for the BP, the equipment they can give unrealistic results, and the doctor might place you on the chronic, whereas it was an instrument which was not calibrated. So today, with calibration, we always check the verification. It's a process where we check that is this instrument, is it still fit for the purpose, for what it was intended for? Okay, let me go back now to the introduction of the metro introduction. In my introduction, all nuclear radiation monitors instruments have strengths and the weaknesses and require reasonable care in use. And we must take care of those instruments because sometimes you can damage the probe, but the instrument is still switching on and off. But when it comes to the readings, other instruments, they are so sophisticated in the way that they can give you abnormal range or readings. That way it can trigger the alarm to say, this instrument is no longer fit for purpose. Other instruments, they don't even go do that. They can remain at low range, reading low range, and it might deceiving you. When there is a high level of radiation, you won't be able to see it because of you are not handling this with care. Other PM tube is a glass tube. If you bang it, that glass tube inside, it will break. I'll show you how it looks like. The lab equipment performance must be traceable to the international system. That is the SI, via the National Meteorology Institute. We've got NIST, NPL, and NRC, and the PTB, and also BIPM. Those are the primary laboratories, of which NIMISA, they send their primary reference standard to any of this laboratory. Once NIMISA calibrated that, as South Africans, NIMISA is the one that disseminates the chain of the traceability to other calibration laboratories. Other calibration laboratory, any other laboratory of which their reference standards are calibrated by NIMISA. So therefore, they are already in the chain of the traceability of measurements to the national measurement of standard. Unlike if the instrument is not calibrated by NIMISA, or it means that that lab already broke the chain of traceability is now broken in a way that measurements cannot be trusted. Why are we supposed to do or perform calibration? There are three main reasons for having the instrument calibrated to ensure readings. We're not doing this for the regulatory body to see that we are complying because we don't want to burn our fingers. We're not doing this to please the regulatory body. And then we keep the certificate or the instrument in the cabinet until when they come to inspect us. We're doing this for the benefit and for the safety of the radiation workers. A radiation worker, it can be anyone who is registered with South African Bureau of Standards wearing a TLD or any other field. People might also have the access to the area where there is a supervised area where there is radioactive material or there is level of radiation. But in that case, they will be relying on the calibrated instrument. In this case, this is the reason why are we supposed to calibrate our instrument, is to ensure the reading from the equipment are consistent with other measurements. Who are the other measurements? National measurement of standard. If my instrument reading, if a calibrated instrument reading should be more or less the same with another calibrated, but differ with the percentage, with the uncertainties from the calibration point, where you will see my colleague was presenting it, where it gives the upper and the lower limit. We also need to determine the accuracy of equipment readings. Accuracy of the equipment reading is the key role. We don't want to be misled by the instrument. And to establish the reliability of the equipment, reliability that it can be trusted. If you trust it, you will never go wrong with your instrument. And then you will also rely on the readings that your instrument is giving. But it is through a maintenance process, but I'll touch it based when I'm going through to my presentation. And then the calibration cover the following: the traceability, relating your measurements to others, which is national measurements of standard. Uncertainty, how accurate are your measurements? Reliability, can I trust this equipment and achieving traceability in your measurement? What calibration certificate contains? Then I will also put that in another end. I've got some certificate to present. I've already emailed them to Mr. Ditole, and I will then ask him to present, to load them after, or I can load them from my side. Calibration is the process of measuring the actual performance of an equipment under test using lab instrument that intends have a significant better performance than equipment under the test, the unit under the test. The instrument that have better significant performance is my reference standard, which is actually calibrated by NEMISA. And then when I calibrate the client or the end user instrument, I'm comparing that instrument with my instrument because it was calibrated by the NMIC. Ionizing radiation is a radiation composed of particles that individually carries enough kinetic energy to liberate electron from an atoms or a molecules to ionize it. And then radioactivity is a natural and spontaneous process by which the unstable atoms of an element emit or radiate excessive energy from a particles or a wave. These emissions are collectively called ionizing radiations. The instrument maintenance. Why are you supposed to look after your instrument? Similarly for the car requires interval preventative maintenance. You service it after or before certain kilometer or actually a month, whatever comes first. And the reason for that, we don't want to be disappointed. Similarly with our instrument, we don't want to be disappointed. The instrument must have a maintenance record. Always check before use. And when you check your instrument before use, it doesn't mean that when it switch on, everything is well, then you can take the field. You need to have a data sheet that you can check the measurements. I will talk about that one as I go through. Use a calibrated instrument always. Have a checked source. It is advisable, especially for surface contamination, similarly for the radiation, except the EPD, that you have your own check source. And check source can be made out of any radioactive materials, which is not a reference, a CRM, reference certified material. And when you have your check source, every time when it is calibrated, they will calibrate it against that check source measurements. They will present those measurements results. Anytime when you take your instrument to the field, you place it against the check source in order for you to see that is it still reproducing your upper limit and the lower limit for the check source. Is it still within the range? If it's still within the range, that gives you the confidence. And you can take your instrument into the field with a happy smile. Records all the measurements for quality controls purpose. Every time when you check the check source measurement, you can record the data and to say, today is reading this, so that you can have a trend of data, which can eventually at the end of the day, tells you whether your instrument is still reliable and whether you can still trust it. Keep record for all the calibration certificate. The calibration certificate, they will actually assist you to check the response and the behavior of your instrument by looking at the calibration factors, and also with the percentage deviation or the uncertainty as reported in the certificate. And keep the instrument measurements, all the records for purpose that it will help you. When the instrument starts reading abnormality, you can even pick it up because you have got a good, nice strength of record. And in most of the instruments, the problem that one can face, when you put the batteries inside your instrument, make sure that you always check when you, or you have a frequency preventative maintenance in a way that sometimes you might find it out that the battery leaks the water and that water is too acidic and the water will damage the internal component of the instrument. And then it will cost you to replace the whole instrument or to buy the new instrument. Now, let me also touch this point of selection of the instrument. When you need to buy the instrument, you are not buying instrument because the regulatory body instructed you to have that instrument. You will have to buy instrument looking at your facility, looking at your place. What nuclides do you have? What types of the radionuclide do you have? And you go according to the instrument. There are certain instruments that can measure alpha betas. There are other instruments that can measure the gamma. Not all instruments can be 2-in-1, but I'll show you the instrument which is 2-in-1, which can measure alpha, beta, gamma, and also instrument which can measure alpha and the beta for surface contamination. And you need to select the instrument which is suit for the area. Unlike in the place where you don't handle, I'm just using as a typical example, you don't handle uranium, but you want to buy instrument which can also actually measure the uranium. So that one will be like a bonus for you, but it won't even help you to measure the nuclides which are actually available, which are actually the area of a concern. You need to learn how to operate your instrument. Read those manuals, get to understand how to change the unity from one unity to other. It is so easy and user-friendly like a phone. Unlike with this smartphone, some of us, especially, we don't know how to operate them. But the young one, the kids, like my son is 3 years old, he can operate my phone like nobody's business. He knows in and out, but he never read the manual. But in this case, we can encourage everyone to understand you read the manual so that you don't have to find yourself damaging your instrument without knowing. And then these are the decisions that actually eventually pushes or makes you to choose the instrument which are fit for purpose. By knowing the types of the nuclides, types of radiation, we have got the alphas. And the alphas, we normally measure them in becquerel per square centimeter. And the beta, we measure them in becquerel per square centimeter. The gamma, you see the unit and the neutrons and the X-rays. So knowing that where in that area, you need to also to identify the types of nuclides that you want to measure. These are the types of the ionizing radiation. This one is the alpha and the betas, and this is their penetration. You could see that if you want to measure the alpha, you cannot stand in a distance of more than 1 meter. You need to be as close as much as you can, where your instrument and the surface object you are scanning should be less than at least 4 millimeter spacer in between, but don't allow your instrument to touch whatever the surface that you want to scan, because if it is contaminated, it contaminates your probe. This one is actually the betas. If you know the strength for the beta, you can actually also know how to measure them, and also the gamma, they've got that stronger penetration, the distance. Like even when we do radiological survey, you can measure from close contact where the spacer must be at least 4 millimeter. Even when we perform calibration, we leave that spacer between the active area of the source and the probe 4 millimeter. Then you'll able to get a nice readings, which can eventually help you to make a decisive decisions. And with the gammas, they've got a strong penetration. Similarly with the neutrons. And with those ones, then you know the type of the instrument. You cannot expect to measure the neutrons with the instrument which measure alpha and the beta. Similarly, the instrument that measure alpha and the beta, it cannot measure the neutrons. So those are the key things that we all need to understand. Doesn't mean that any radiological instrument can pick up any radiation. There are actually radiations are classified according to their strength, and the instrument does work the same. This is the type of the detectors, what you will see or what it is there inside your instrument. I also indicate that for the detector, you have only 3 components. You have got the power supply, which is the voltage. And you also have the cathode and the anode. When the incident ionizing radiation entered this one, this is how you see, and then you get the readout, which actually give you this actually process. It is happening inside the gas detector, and then this process, it is happening in the gigamolar tube, because gigamolar tube doesn't have the P10 gas. This is the scintillation detector, the one that the glass that I even mentioned that. And this glass, it is meant for the instrument which measures alpha and the beta. And if you bang the probe, then this glass tube, it will break, and it's quite sensitive and also a bit more expensive. It might even cost you plus or minus 15,000 if it is broken. And this is the type of your ionization chamber. Voltage. When instrument is calibrated, we set up, especially for surface contamination monitor, we set up the operating high voltage. And that high voltage, and it will be defined in setting before in the certificate and setting after. There's a table which actually shows you all the settings. Please, please, I'm begging and I'm pleading with everyone. When you see a settings before and setting after, make sure that when you take your instrument for QC and also to take it to the field, make sure that your settings correspond with the setting after calibrations. If the settings are, once you alter other key parameters like high voltage, it invalidates the calibration. But the sticker, it must be still there, but the instrument is no longer fit for purpose. And those measurements that what you will get, they will be no longer be traceable to the national measurement of standard. This is you could see the HV that you can set for the alpha and the beta. For alpha, it's quite high because it's easy to pick up the alpha. The alpha can be stopped with your skin or even with the paper. So that is why you could even see the HV there. And then now with the beta, you can also have the HV at certain level and also the gamma. In this part, this is the part where you have your gas proportional counter, the detector that I was showing you, it operates at this energy, at these high voltage levels. As you can see, you start from 1 and then you are increasing the high voltage. And from this is the limited gas counter proportional detector of the detector. And this is your gigamolar. The gigamolar is the one that we normally we say GM tube. It's a gigamolar tube. That is the one that you used it for radiation survey. Most of them, they've got the GM tube. That is gigamolar tube. Calibration requirements. Laboratory develop the work instruction for performing calibration according to ISO 17025. If the laboratory is accredited, we perform the preliminary check. Preliminary check is to check if the instrument is still working fine. Is everything's okay, and calibration performed under controlled environment. And the set requirement for temperature is 20 plus or minus 5 according to SANAS TR 18. And we also check the functionality. When you check the functionality check, that is when you check the instrument. Is it still doing everything according to what manufacturer or according to what it was actually intended or designed for? And we record the parameters before we commence with the calibrations. We do the background measurements, and I could see that in most or in the field, when people are going to take the measurements, in most cases, you'll notice that, sorry, excuse me, background is not taken into consideration. Please take the background, especially in the white area. White area, that is the area where there's low radiation background, so that when you take the measurements from the field, you can subtract your background measurements to get the actual measurements. Because the reason why we encourage people to take the background measurements, other areas or other houses were built with radioactive materials, and the instrument tends to, when you go to the field, you tend to get a high readings. Count rate alarm test, and then you also test. Is still this one triggering the alarm when there is excessive radiation and they respond to contamination? Those are the for instruments which have that functionality, not for all the instruments. The types of the surface contamination monitors. These are is a list what I can show here. There are many instruments which measure surface contamination. We have got the CM9 and the CM11. These are the instruments that we use them for the barrier monitor. Barrier monitor is when you move from one area to another. Unlike for nuclear medicine department, they've got a hot cell. When you leave the hot cell, you can use also this CM9 to scan yourself to make sure that you are not contaminated. Electra. With Electra, we've got Electra 1A and we've got Electra GM. Electra GM is an instrument with 2-in-1. It can measure radiation survey. It can also measure surface contamination, lucent contamination. And then we've got the SX. The SX is actually the replacement of the Electra 1A. And then the SX connected with the pancake probes. This is the one which replaced the Electra GM. Because with this instrument, it comes with with one pancake probe, GM gigamolar tube, and also with a radiation survey probe. And the instrument is calibrated with 2 probes simultaneously. We start with the contamination and then with the radiation. And on that note, the instrument which is also eventually calibrated with a probe, if you have got more than 2 or 3 instruments which are similar, and then it happened that one instrument is not functioning or it becomes malfunctioning, you cannot swap the probe. It is strictly prohibited. The settings for that instrument were meant for that specific probe which was calibrated with instrument. In most cases, the people they end up saying that no, because the other probe was calibrated, therefore we can swap. No, you cannot swap because the settings won't be the same. Rather send it back to the calibration laboratory, they will calibrate with the probe which is working in case if another probe is damaged or the instrument is damaged. Also, when instrument undergo a repair, it also plays the role to say, do I have to resend my instrument for verification or for recalibration? And when do I have to take my instrument for recalibration? Only when you replace the major component part. If you replace the whole circuit board, unlike with these ones that we always see these days, then you don't have any option except to recalibrate your instrument. You replace your gigamolar tube, your instrument must be recalibrated again. You replace the PM tube, your instrument must be recalibrated again. So you will understand those dynamics. We also have the hand and foot monitors, which most of them, yeah, many suppliers, they do have like different brand, Berthold, Canberra's. There are many, and then also the whole body counter with 35 gas detectors or scintillation detectors. And we have got the red eye HEC handy counter. This is the instrument which is eventually designed and meant to measure for the when you want to perform the leak test, but I'll touch that during my presentation. And we also have the Berthold LB123, and there are many instruments within this space. I just want to, this is the B20. This instrument, it is actually 2-in-1. It can measure surface contamination, which surface contamination alpha and the beta, where the unit it will be in becquerel per square centimeter. Or it can measure the radiation, where the unit it will be in microsievert. So this is the contamination. It measure becquerel per. It measure surface contamination. And this is a flow detector where is an actual scintillator detector. There's a tube inside that tube that I was saying that if it breaks, then the instrument is no longer fit for the purpose. And the unit, when you scan the flow, it will be in the becquerel per square centimeter. This is the likes of the CM9 and the CM11, how they look like. And this is the probe. You take the probe, you scan around your body. This is the instrument which is fit to check to determine when if you have got so many sealed sources or X-rays, you can also use this instrument to check the content or the level of radiation when you perform the radiation leak test. These are the hand and foot monitors, and this is another typical example of the instrument which measure surface contamination monitor. That is why you see the units in counts per second. Also, it is very important to know the units. Units for surface contamination monitor counts per second or becquerel per square centimeter. You will able to call if the instrument measure in counts per second, you will have to be able to convert your readings from counts per second to becquerel per square centimeter, because the guideline from ICRP 60, it is stipulated the levels of radiation in becquerel per square centimeter. That is the reason. Yes.
May I interject? Please take note of time, sir, and if you can quickly try to address also the issue of certificates, in particular the measurements as well,
yes,
as the time is not on our side.
Okay, according to my uncalibrated chronometer is
sorry, sir. Sorry, sir.
How many minutes left?
Yes, you are left with 10 minutes. May I request Wendy, Wendy, if you're still on the line, I've tried to attend to some questions on the chats. In the interest of saving time, please go through some of the questions if I did not able to attend to, or I might not have seen them, and answer them, so that at least by the time we are done, we have attended to a lot of questions on the chat. Thank you, sir. You are left with 10 minutes.
Okay, right. Thank you. I will actually check if in my uncalibrated chronometer to make sure that I'm within the time. Okay, this is the high voltage plot that we determine when we perform the calibration, and then we set according to the data. And that is why we emphasize that this should not be changed. Even here, we set this one at 840 volt. And these were the count rates which we actually determined that. And we're using nuclides to determine that. We perform also the linearity with the cesium source. In the certificate, we determine the percentage activity response. You will see the surface activity response, 2 pi, rejection factor, like I've said, cesium. This is the content in the certificate. These are the settings before, when the instrument comes. It is quite embarrassing, and it's quite actually disturbing to see instrument comes with 20 volt here, and meaning that you can't measure anything if it is set like that. And this is the setting after. The setting after, these are the settings that you use every time when you take your instrument to the field. And this one is the parameters that when you set your instrument from counts per second to becquerel per square centimeter, you go to parameter 9 for Electra, then you go for the alpha, you set that one. Similarly for the beta, you do the same. And then this is also the result that what you will see, the percentage activity response, and also the 2 pi efficiency from your certificate. And how to convert your instrument from counts per second to becquerel using the calibration certificate. You use this the percentage activity parameters. The instrument setting, you select parameter. That is what I've said before, and then you enter the correct. You enter these readings, and then you save them. They will stay in the memory and the instrument every time when you go to becquerel per square centimeter, it will remember those settings. The measurements uncertainties, I won't talk much due to the limited of time, and I'm also welcome for the other questions. This is the type of this is the Electra. This is where inside there is that glass sensitive PM tube. This probe is 49 square centimeter. This one is 100 square centimeter. This is the traceability chart, like what I've said, that NIMISA. This is the primary laboratories, the likes of the NPL, BIPM, BDB, the yes, NIMISA, then we've got the ACHEMAS, they've got ACHEMAS standard and the particle emission rates, and that is when other labs comes in, all the calibration laboratory. We get it from the ACHEMA or particle emission rate, and then it goes to the end user of the facility. This is the pyramid just for the traceability that there is also national measurement of standard, primary, NMI, and then it gets to the standards accredited laboratory, and then it goes to the end user. And then the importance of using the check source. Why do we need to check the instrument? Also to make sure that my instrument is still measuring the same. For functionality test, why do we perform the functionality test before use? The instrument, it has not been used for quite some time, but sometimes when you switch it on, it can give you readings, but those readings, for you to be sure, you need to test them against your check source. Use instrument with the calibration certificate. Never swapped the probe or swapped anything, like what I've said before. What does the uncertainty of measurements mean to you? How accuracy close to the actual measurements? What do you need to measure the radius? This is okay. Now, this is the EPD. This is the actually critical part. Most of the EPDs, you could see different type. This is the pen EPD. We call it a QFD. You could even see all variety. And this is also a thermoscientific is quite strong one, Siemens one. This, you see all the variety. And what does this instrument measure? They measure dose. You cannot substitute this instrument with an instrument which measure exposure rates, unlike the ones that I showed you before. Other instruments, they are meant for measuring exposure rates. This one, it measures accumulated dose per hour. That is why if it is measuring or reading 20 microsievert, it means that in an hour, your body will be already absorbed a dose of 20 sievert and then microsievert. So in that instrument, when we calibrate it, we use we also use we do use the soft gamma, where we use the americium, and also we use the cesium. And then with the cesium and the americium, we're determining the energy response factor. The energy response factor, a good energy response factor varies from 0.67 to 1.5. So if you look at 1,32 for this specific instrument, it shows that the instrument, it is still in good conditions. This is the instrument, the readings that you will see. This is your instrument respond, and this is the true dose. The instrument was given this dose over a time, and then the instrument produced that. And this is the percentage deviation, and that is the uncertainty plus or minus 12 that you can determine your upper and the lower limit when you apply the uncertainties. These are actually the results, and this is the overall result of the percentage deviation. If you look at our guidelines or TR18, the average percentage deviation should not exceed plus or minus 15. And the single percentage deviation, that is intrinsic error, it is there in your certificate at the bottom of each table. From all the laboratories, you will see that. This is the intrinsic error. This point for single point of measurement should not exceed plus or minus 25. And those are the values, or those are the keys that we make of the determination of pass or fail. How to perform the radiation leak test. Only sealed radiation source, you wipe around the container, and then you take the measurement for the swab paper. You use the instrument that I showed you, and analyze and make the determinations. For you to make the determinations, you need also to know what do you need to, you need also to know the reference levels. And the calibration frequency, this is the government gazetted number 15496. 26 February 1993. It is so clear that the calibration EPD is 24 months plus two grace period, and surface contamination 12 months plus 2 grace period. This is how you perform. But when you place this is a paper. You wipe this paper around your source or X-ray to check if there is a leakage. But the distance between the surface active area of the probe and that source should be at least as close as much as you can, by at least 4 millimeters. But you shouldn't touch in case if there is a leakage and that paper is contaminated, then it will contaminate your probe. And then your instrument must be in becquerel per square centimeter, as you can see here. I've lifted these probes higher so that you can see nicely what is the paper, actually the one that you perform the leak test. It is at the center of the probe. And then the radiation levels determined by the ICRP guidelines. And for alpha, that is 0.01 becquerel per square centimeter, and the beta is 0.4 becquerel per square centimeter. And then if you look at the role and the responsibility for the RPO performs job safety evaluation project process or procedure in order to identify, assess, or control, protect personnel against radiological hazard, provide radiation protection services, and check advice directly to the nuclear facility manager and personnel, and then invigilating of radiation protection related activities in the facility, invigilating and monitoring the operation. Those are the actually in overall the role of the RPO, and issuing the work permit for the non-radiation workers when they are accessing the control area. And then what is the RPS? The RPS is radiation protection specialist, and their role established the RPO policy and the system, ensure that in Nexa we've got a program where the RPS actually actively rolled, but in most cases, especially the hospital, you want to know the role of the RPS, but this is the overall responsibility. The RPO reports to the RPS in order for the decision and everything, whatever. And then I thank you. Before maybe I can, I don't know, Mr. Ditola, if I still have time, I would like you to present, to show one certificate.
Yes, sir. Can you do it in the next 4 minutes? We actually run out of time, sir, because that's the most important part that our
okay.
people needs to.
Mr. Ditola, I think, okay. Let me just go to that one before, without waste of time. Or in the digital, I email you a certificate number 9602. Can you also project it from your side, if so?
I will have to to quickly check on that.
Yes, that is yeah, there is a reason why I need that certificate to be actually displayed here. There is something.
Which one is that?
9602. 9602. There is another part where we report the two tables. So I need to emphasize in those two tables, what are those tables for in case if any of the end user might have the B20, which is actually a good instrument.
I'm projecting your certificate.
Yes, thank you very much. Then scroll down to the table. These are actually the details of the instrument, the environmental conditions. Yes, okay, thank you very much. Yeah, you can stop here. I wanted to emphasize here with these two tables. Okay, thank you, Mr. Ditole. This is a table for without the alpha filter. B20, it comes with the alpha filter. You put it in front of the instrument. When we put it in front of the instrument, we calibrate instrument, and these are the percentage activity response, and all this is the values that you set inside the instrument through parameters, so that when you go to becquerel per square centimeter, it takes these par values in order for you to give you in becquerel per square centimeter. If you are using instrument without that alpha filter, this is your measurements that you can, this is the parameter that you can set in the instrument if you have a software. But if you don't have a software, you can tell us, and then you said, no, I don't use this instrument with alpha filter, but normally when it left, we always set it without a filter, without the alpha filter. Alpha filter, it is a package that comes with the instrument. So if it comes without that, we can also set the instrument to this parameter so that you can be able to use it. And then you can scroll down. I also want to the certificate. Okay, those are the tolerance values. Scroll again. Okay, I think these are actually the raw data. Can you also project 9650? That one is for the, but I think even though, I don't think I still have time, Mr. Ditole. I think
you need to quickly go through the EPD ones. Did you send it?
Yes, I did send you the one that.
Which one is that one for the
last
EPD?
email, I didn't name I didn't name it. I just forward you the email with EPD. It is yeah, it's a scan copy actually. So that one, it was a scan copy. The last email I forwarded it to you this morning. Did you see that one? The attachment is not named. So it's actually something. If you look at the attachment, it's SC308 times 2. You could see that.
Projecting it, you need to, I'll go to the measurements.
And then these are the details of the instrument. Like what my, okay, you can stop it here. I want to show this table. Like, and then also this factor. My colleague here, Wendy, Miss Toka, actually, she eventually touched these bases. And then you could even see that what NIMISA is doing, and we are actually all the labs doing the same to show that we are guided by the standard. There are also international standards which are guiding us when we perform the calibrations. These are the factors that we imply them or we put them when we deal with the egg hammer. And then let me see this table, the ones, yeah, the table below. This is the table where you determine, so this is the, no, not this one. Go up a bit. Okay, thank you. This is the table where you determine your energy response factor, and a good energy response factor should be within this limit. And then you could even see with this one that this is the formula factor, instrument readings for americium divided by the instrument readings for cesium, also multiplied by the true dose for cesium and divided by the true dose of americium. It gives us this value. Scroll to the next page, to the next table. Okay, thank you. Scroll a bit down. Okay, thank you, Mr. Titole. This is the table which shows it's more or less the same table that I presented in the results, that the instrument respond, it was 2 microsievert, and the dose given to the instrument was 2.1, and then the percentage deviation, that is the intrinsic error, is 4.90, and this is the uncertainty, which is plus or minus 12. And then also, if you look at similarly for 5, this is the true dose, and this is what the instrument was reading, true dose, and the instrument was producing that. Here it is this true dose, and you could see that most of the EPD, they are quite accuracy. And up until so, like the single point, scroll down, scroll up a bit. I want to show these formulas. Okay, no, so sorry, up, scroll up, sorry, Mr. Titole. Scroll up again to that table where, no, go up, no, you're going down. You go up. Sorry, Mr. Mutolo, let's go to the next page, not this one. Let's go to page 3.
Oh, I should go down, not up, sir.
Oh, sorry, yeah. Let's page more to another page. Okay, yeah, page up a bit. I want to show, here's the formula below, that your percentage deviation, measured true dose, measured dose minus the true dose divided by the true dose multiplied by 100. That is what determines this. And then also, it is also clear and stated, individual deviation must be better than plus or minus 25 for single point of measurements. And also for the average is plus or minus 15. That is what I was saying. And this is our uncertainty. We state it according to the GAM. And then let's go to the next page. And from here, those are the remarks and also the calibration frequency. Now this is the raw data. And then I thank you everyone for actually allowing me to share this presentation with you. For me, it was an honor. Thank you, the organizers and Titole together with your colleagues. Thank you.
Thank you, Marius. Colleagues, I would like to take questions at this point. Ntokozo, can you give me a heads up if your participants are able to turn on their mic?
Let me change that. Give me a sec.
Yes, and they will have to raise their hands so that we can take questions sequentially. Please let's have a bit of order when it comes to that. Please raise your hand so that you can be identified, and our presenters will able to attend to your questions. Thank you. Let me know once they are able to turn on their mic. So long you can raise up your hands.
We are good to go.
So that we can, please, Ntogos, assist me if you see any hand for questions.
There are no hands yet.
Any questions? Phineas, you may go through. Sir.
Raise my hand.
I see you, and then Freddy after Phineas. And then after Freddy, we'll ask the presenters to respond to the questions, and then we'll take another row of hands. Phineas, Freddy?
Yes, thank you, sir. I just wanted for clarification if our laboratories do report any deviation that is above 10%, because according to our regulation 1332, it stipulates that when the check shows a variation of more than 10%, the instrument must be recalibrated. I couldn't really get it clear whether those variations are they reported in their calibrations processes or not. Thank you.
Ready?
Can I proceed?
Yes, sir.
Hi, how are you guys?
Good yourself, sir. Please
Good,
go ahead.
I've actually posted the questions that I have, but I haven't received any response to it. So just wanted to find out from the presenters when is it considered a repair? Because if you adjusting dead time and sensitivity on a on a radiation monitor of sorts? Is that considered part of calibration or repair? And then secondly, as well, at what point is the laboratory's uncertainty not acceptable? Because obviously there's a whole range of different uncertainties from the laboratory itself. And at what point is it no longer acceptable to have that maybe a big uncertainty? And then my last one, yeah, that's it. Thank you very much.
Wendy, do you want to come first? Wendy, Marius, maybe you may try to respond on the questions that have been posed. Seems like Wendy, she's struggling.
Okay, thanks.
Okay, I'm here.
Okay.
Can you hear me?
Yes, ma'am. Yes, ma'am.
All right. Thank you so much, Ditole, and thank you to the colleagues for the questions. Going to the first one of the variations, in the calibration labs, we do not report the variations. Rather, we report the measurements uncertainties. And the compliance that we see is as per document that we use as the guidelines. For example, in terms of when we say an instrument is not complying, there is a technical report document that as the accredited labs we comply to, called TR18, which actually stipulates when we can say the instrument conforms or it doesn't conform. And that a guideline, it's actually guided by the international standards like your IEC and the ISO. I'm not sure if I have answered everything that you needed to know.
Please go to the next questions, the ones that Freddie raised.
Okay, and in terms of adjusting, repairing, and all that, let's, for example, we have, because now actually the adjustments are actually seen on the analog meters that recently are sort of phasing out. That's when we actually are able to perform to do the adjustment on an instrument. Those instruments will have a potentiometer that we will need to adjust. But we need to keep in mind that adjustment is not calibrating. After adjusting that potentiometer, what we need to go back again, we need to go and look at what the definition of calibration means. Calibration means that you compare the known to the unknown at certain uncertainties under a controlled area, and whatever that you are comparing to is the national measurement standard that you are going to be comparing your measurement to. So that means that even when we adjust, if I get an instrument and just adjust it and say, okay, I've adjusted it, now it can read 20 that I want. That doesn't mean that I have calibrated it. I still have, after adjusting that potentiometer, to go back and put it in the beam again and go through the process of calibration again. And also, if we look at our commonly used meters now, which are the digitals, that those meters don't actually, most of them don't give us that liberty to go in and adjust and everything. That's when now, when things don't go right, we will recommend for repairs, of which repairs are done by someone who is competent to perform that kind of repair, not just the lab. The labs we do not repair, we only perform calibration. Thank you very much.
Maybe you can attend to when is the uncertainty acceptable?
Oh, yes. Okay, the uncertainty part. When it comes to the uncertainty part, we cannot really say your uncertainty is unacceptable. Remember, the uncertainty comes from the traceability chain. So the traceability chain starts with an SI unit or a primary standard. And then it goes down to another level of a secondary standard or a national measurement standard. And it further goes to the accredited lab and eventually to your end user, which might be the industry. So when we look at the chain, as the chain goes down, the uncertainty increases. So for example, for NIMISA, we go and calibrate our measurement standard against the primary standard. And then we're going to come up maybe with an uncertainty of 2% or 1% that comes from the primary standard. And when we come back into the lab, we are going to incorporate the value that was given by the primary lab into our uncertainty budget, which means that value that we got, it's actually going to increase, because when we do the uncertainty budget, we're looking at every other thing that is going to have an effect towards your measurement. Number one being the standard that we are using, the conditions under which we're working, the person who is actually performing the measurements, the repeatability of that instrument, how the reproducibility of that instrument. So there is a lot of factors that actually come into play when we come to uncertainty. And then combining that, then you will end up with a big uncertainty, or whatever uncertainty that you get as you go down the chain of traceability. And we also have to take note that the values close to the SI units, they are the ones that are smaller. But as you move further from the SI unit, then everything increases. So that being said, we cannot say, for example, if you give a 20% uncertainty, we can say that is unacceptable. So that is based on the conditions under which the measurements are taken, considering everything that will impact your measurements. Thank you.
Thank you. I'll take the next questions and then maybe Maras will attend to them. Thomas Sibia, and then we took Fred, and then Mudisenyane will follow after that.
Thanks, Chairperson. Here, Thomas Sibia. It's not necessarily a question for my side, but rather a request. Is it possible, Chair, that you can share the presentation together with a demonstration of certificate that has been made for this session? Thank you.
Okay, thank you. Yes, I think I did mention that on our charts that the presentations, both the presentations and the recordings, will upload them on our site. I will quickly show you how to access them on our site after the last questions, so that you can able to indulge at your own free time. Mudisenyane?
Thank you, Chair. I have one question and one concern. My first question will be, is it possible, or is there a way that we can send, let's say, those calibrators, for instance, for calibration? Or yes, that's my first question. Then the second thing that I have is a concern. I just want to hear from Wendy. It's a problematic for us as government institutions to register on their system. I'm not sure whether I am the only one who's having troubles, or is there other people here from public sector who are having problem registering at NIMISA, because this system that they're using now, it just frustrated us, and remember, it's a requirement from SAHPRA to have this instrument sent to for calibration. Thank you.
Thank you, sir. The first question, I'm not sure if radioactivity, Jolene, I think I've seen you somewhere. Do you have any response to that? Any future plans for the dose calibrator? Is there anyone from radioactivity? Wendy, do you have your colleagues?
Yes, the dose calibrators are actually handled by our lab that is based in Cape Town. So if you need them calibrated, you can actually just contact them. There's Jolene, there's Martin, and there's also Milton. So if it's okay to just share, you can contact them on radioactivity@nimisa.org. So they will give you all the information in terms of the logistics of calibrating the dose calibrators.
Thank you, ma'am. The question about your system, I guess it will be good if you can just try to contact NIMISA separately so that they can assist you on that request to able to register on their portals. I hope that you can also check with Wendy as well to assist you on that request. Freddie, do you have any questions, sir? Because I still see that your hands is still up.
Yeah, I just wanted to add to obviously the response and my how can I say, the findings that I get on my side, and maybe just to update the laboratories and see if there's a different way of looking at this going forward. So in my experience, so even the digital units, I'll take for example, sorry man, I'll take for example a SE unit, right? So the SE digital units that I've been receiving. So what happens is on the unit, you've got dead time and obviously sensitivities that is utilized to bring the unit within calibration, right? So I've discovered on my side that units would go to a certified laboratory and then come back stating that the unit needs to be repaired. So from a client point of view, he sees the unit as being faulty, you understand? So they return it for repair. But in essence, when we test and set up, it's actually just adjusting the dead time and the sensitivity. And also a lot of the manufacturers actually specifies adjusting these dead time and sensitivities to bring the unit in within calibration. So saying that adjusting is not part of calibration, but the manufacturers are essentially developing things in a way that you need to adjust this. So as your detector gets older, whatever, you need to bring that within specification again, you understand, as part of their calibration process, you understand. But we've just been that's one thing that I've picked up on my side, where we then adjust the dead time and the sensitivity and then send it again for calibration, and it succeeds, you understand. So maybe just I don't know if you've got comment or findings around that, or maybe the wording is something that we need to look at or something like that. Thank you very much.
Thank you, Freddie. I don't know, Marius, do you have a minute that you can try to respond on this? Otherwise, we'll ask Freddie to engage with you guys further on this. It seems like it's something that it needs a lengthy time to attend to.
Okay, thank you, Chair. I will also want to reflect to what determine the CMC for the laboratory calibration measurements capabilities.
Please try to squeeze it in a minute, say we have exceeded our time.
Yes, that actually informs by the what you call the sources of errors. What other human errors or sources of error that contribute or affecting you not to achieve the 100% results? Having the sources of errors, it will determine you'll be able to determine your CMC. Coming into the repairs, yeah, if adjusting a sensitivity or the dead time is one of those factors that we sometimes adjust for certain instrument, they do allow that, and then they pass calibration. And what informs that the instrument did not pass the calibration is when the single measurements percentage deviation, we normally take up to 10 or 20 readings. When it is the percentage deviation is above the set limit of plus or minus 25%. for single point of measurements. And then we can even tell you that even your instrument is not stable, it always fluctuates or sometimes it saturates. We can advise you, especially when the detector or the GM tube, when it gets aging, it starts becoming saturating very fast. Thank you, Chair.
Thank you, sir. I would like to close questions. If you have any questions, the presenters are welcome to. They said that you are welcome to contact them for further indulgement on questions that you might have. We understand that we might not have covered everything that you would have wished, but we hope that this was a platform to open up so that you can able to address certain questions that you encounter. Please note that we've got a questionnaire pool to rate the presentations, the webinar, and how the content, how was the content? If you're able to appreciate the content, did it meet your expectation? I will quickly try to show you where we're going to upload the presentation and the recordings. So when you go to our website, SAHPRA, you go to news. Okay, can you see my screen to start with? Is my
Yes,
screen?
we can.
Thank you.
Yes, we can.
When you log into our SAHPRA page, go to news, events, and then you click on the event, and then you will notice there it will be under this page. If you click this page, we'll upload it somewhere there. We haven't uploaded it yet, but it will be under this page to access the material of this webinar. At this point, I'd like to thank you all. I hope this was fruitful, and will also encourage you, if you have other trainings that you might want radiation control to offer you, you are welcome to send us an email to look into such trainings. I'll give this time to my manager, Nico. And I also saw our manager, Ms. Kapi. I don't know if she's still around on the call. If she's around, I guess then maybe she might also want to say one or two. Nico, thanks, sir.
Thank you, Ditole. I really want to thank the presenters for the excellent presentations that they gave us. I don't want to spend a lot of time now, but please, I ask the participants in this webinar to contact us if there's any more questions, but also with suggestions of similar webinars that we can address other issues that you might have. I thank you, and you must have a wonderful day. I don't know if Ms. Klape is available and if she wants to say something.
Ms. Klape, are you on the call? It doesn't seem like our manager. She's around. I want to thank you all once again. Please enjoy the rest of your day. Thank you all. Bye.
Thank you. Bye.
Bye-bye.
Have a wonderful day. Bye-bye.
Bye.
Thanks you all.
Bye.
Bye.